Now here's a comparison of the classic spectrogram in the upper left and the specific loudness spectrogram in the lower right, just so you can see them right next to each other. And also shown are the intermediate stages on the way to the specific loudness spectrogram. So classic here, and then just multi-resolution here, before the smoothing, before the resampling. And then here's the excitation pattern, which has the smoothing and resampling in it. And then finally the specific loudness, which is the non-linearly enhanced excitation pattern. And so you can stare at these and get a feel for the differences. One thing you really see is that the classic spectrogram gives you much more information toward resolving harmonics and estimating fundamental frequency and that sort of thing. And so it is an example of when you would use the classic spectrogram over the perceptual spectrogram, right? If you really want to know the pitch, you want to know the harmonic frequencies, why give up that information, right? You would want to go ahead and use all of the information you have toward estimating pitch and overtone frequency. But if you want something more perceptual, let's say you're using this as a feature in a music information retrieval system, you want to have the same correct and incorrect classifications as the human brain, then you want to stay close to perception, and you don't want to over-resolve the spectrum. You want to go ahead and let time resolution kick in. So you have good frequency resolution at low frequencies, and at high frequencies you want to trade that for high time resolution. But hey, why don't we do better than a brain and have both of them, right? You could have a high frequency resolution spectrogram and a high time resolution spectrogram, and any number of them in between. You can have any number of time resolution trade-offs and use them all jointly as features. And then you have this super brain that can do way better than a human. So don't forget about that possibility. We don't have to limit ourselves to what people do. We should be able to do as well and better. So it depends on your situation whether or not you want to really match perception. Now, I will normally want a specific loudness spectrogram if what I'm doing is evaluating the quality of a synthesizer, right? Because I want to see what the brain sees. Because what I'm trying to do is match this spectrogram, because that's what's getting fed to the brain. And if I can match that with my synthesis, then it should sound the same, because that's the information that's getting into the brain. So for quality evaluation, I really believe in the perceptual spectrograms. But for estimation of parameters, I use whatever spectrogram I can. And I change the frequency and time resolution to fit the problem and to fit the question. And so you can dial it up to whatever is best for the problem. You just optimize the parameters for the given estimator that you're constructing.